Okay, so in today's lab tutorial, we're going to be doing Galileo's experiment, which is also known as the car and ramp or the inclined plane. So the purpose of this experiment is to test Galileo's hypothesis using the equation distance equals 1/2 at squared plus VIT. Now something that we're going to keep constant today is V initial. And V initial is always going to be 0, so that takes that part of the equation out. So now we just have distance equals 1/2 at squared. A few things you'll need today is an inclined plane that's adjustable, a timer with both electric eye A and B, a car with a wing, and a metric ruler. A new piece of equipment for you would be the CPO timer. Now, the way the CPO timer works is it's connected to two eyes, electric eye A and electric eye B. Something to keep in mind is that the timer's error is 0.00005 seconds. Now, let's just take a random number, for example. Let's say that the timer recorded 0.1375. Now, something the timer doesn't do is add on that extra guess that we always add on. Now, we're guaranteed that the ending number is somewhere between 0 and 4, because if it were 5 or above, the timer would just round up. So our best guess to make would be 0. So the way the timers actually keep time is by using the wing on the car. So the way it works is that there's like this invisible beam with both eyes. And the timer starts when the car breaks that invisible beam. So you'll see it. There's actually a light on the top of the eye that will change from green to red as soon as the beam's broken. So the time that we're going to keep in mind when we're doing this experiment is time AB. Now the timer gives off 3 different times, but the only one we're going to worry about is AB. Now time AB is the distance it takes the car, or the time it takes the car to get from IA to pass through IB. To make V initial as close to 0 as we possibly can, we need to start the car at the beginning of our experiment as close to IA as it can without breaking the beam, because as soon as the beam's broken, the timer begins. As you proceed through this lab, you're going to fill in the data tables supplied in the worksheet, record the distance the car traveled and the 3 times to travel that distance. Do this for the 5 different distances down the ramp. Now you're going to repeat this entire process, but what you're going to do is change the length between IA and IB. So, for example, you'll change it from 40 to 50. And now with this data, what you're going to do is you're going to solve to see if the acceleration is constant, like what Galileo's hypothesis is. For each set of time and distance measurements, check to see if the ratio of the distance traveled, which is D, to the square of the time traveled, that distance, T squared. And you want to make sure that it's constant. And make sure that all 5 ratios are the same. For each set of data, what you're going to do is you're going to make a distance traveled, which is D, versus the time squared, which is T squared graph. Okay, so this next step is just for the honors students. It's similar to the first part of the lab, but in this, instead of changing the distance between the 2 eyes, we're going to change the angle of the inclined plane. You're going to do this process for 10 degrees, 20 degrees, 30 degrees, 40 degrees, and 50 degrees. And you're going to want to make sure that you use a protractor to make sure that the angle's right. To solve for the acceleration of the car, what you do is you compute 2d over t squared, and that'll give you the acceleration. With that data, you're going to plot an acceleration versus the sine of the angle on a graph. Now, this graph should give you a straight line, which will allow you to predict what the acceleration would be at 90 degrees. Now, hopefully, it'll be 9.8, which is the gravitational pull.